So hello, and so this is a simple ICTP course. So let me try to. Okay, I think yes. So it's a simple ICTP course, and it's a dual equations and integrable system, and this is part of the fellowships, simple ICTP research in past fellowship. So I would like to take this opportunity to say thank you to Simple and ICTP, and also my host for the research program, Professor Boris Kruklikov, and also everyone at the Geometry and Mathematical Physics group of the UiT, the Arctic University of Norway, for their warm hospitality. And also, I'd like to thank Professor Cordin Reiner of the Lee Stormer Center, who organized this lecture. And let me start by, telling you about the references for this lecture. So for all the content in this lecture, I refer to these. These are main references. So the first four, let me just try to see. Okay, so the first four are textbooks about anti-self-dual equations and twistor theory and their relation to integrable systems. But then the later two are the textbook about differential geometry that I refer to when I record about definitions and theorems that will be used. Okay. So now let me start. So this course is anti-self-dual equation and integrable system. Okay. So I should start by saying what I mean by anti-self-dual equations. So by this, I mean two equations. So the first one is anti-self-dual Youngman's equation. And the second one is the anti-self-dual condition for conformal structures. So by anti-self-dual equations in my title, I mean these two equations, both in 4 dimensions. And for integrable systems, let me start by just saying what I mean by integrable systems. So in this lecture, I use the term integrable systems in a very broad sense that, I mean, the nonlinear differential equations that in principle can be solved analytically. So what I mean by this, I mean that, so there are a general method to generate a large class of solutions, or yeah. So by this, I mean, we would say that a differential equation or a system differential equation is integrable if there is a oh, I'm sorry, I just have to go to the, if there exists a general method that can be used to solve this equation. So a large class of solution can be constructed explicitly and often in terms of elementary or known functions. Yes, or sometimes, so often in terms of known function. By some general method. So this is integrable systems form a tiny portion of the, if you think of the whole differential equations. So they are very rare. So most nonlinear differential equations are not integrable. Nevertheless, they are quite interesting, and they draw a lot of attention of researchers to study them because just because they can be solved analytically. Then, for example, if there is I'm recording. I'm sorry.
I'm teaching.
Ah,
I don't know.
right.
Why look at you there?
Right. Let me continue for the moment. Yes. Okay. So I was saying that although the integrable systems are very rare, but they're interesting and people study them because just because it's really nice to be able to construct solutions explicitly. And although suppose you have a physical phenomena that that you can model by integrable systems, then you would be able to have an explicit solutions that you can analyze easily. So let me just give you an example. And this example, so let me just go back to the reference. So so in this lecture, the theorem and examples I took from this reference, and if I will cite them in, for example, for the examples of integrable system I will use is from this book by Donofsky. So I will just write like this. This is from the book. So, for example, one of it's a very famous integrable system that model physical phenomenon is the KDV. The Portal and the Vries. Or the KDV equation. This equation. So this equation was derived by Korteweg and de Vries to model as it's a water movement, so it is called solitary waves. Let me just explain this. So this is derived. This equation is derived by Korteweg and de Vries. So in 1895 to model solitary waves. In a shallow water channel. So what I mean by solitary waves, so normally when you think of the waves, say like waves in ocean, you would have some oscillations, right? The waves like oscillation. But then a solitary waves is like a heap of water that like a lump of water, and it just moves and retains its shape just like that for a long time. So this phenomenon was observed quite sometimes before Korteweg and de Vries derived this equation. So it was documented, observed and documented by J. Scott Russell. in 1844. So quite some times ago, but then Poitre de Vries then tried to model this phenomenon and derive this equation. And it turns out that this equation is integrable. So a lot of solutions can be generated. And one solution is, let me just give you an example. So the solution is called one soliton. So soliton solution is, roughly speaking, it is a solution that with well-behaved profile. I will show you some movie, like some picture that you will see what I mean. One soliton solution. So this one. So what I write is a solution of the KdV. So C and K are constants. And let me just, let me show you what this solutions look like. It is, you can check it is a solution of the KdV equation. And it's model this solitary waves I mentioned. Let me try to open. Okay. But I have to share this to you. So I stop share this one, and then okay. Yes, you see. Oops. Wait, sorry. It's yes. So what you see here is actually minus u, minus the solution. Or go back to solution to see, but and it's like this lump, and that moves, and why it moves is just retain its shape. Right. So let's stop share this. Okay. Yes. So what I plot there was minus u, because u is negative here. But then with minus you have that shape that you just saw, and it's I have to plot that because it's like water. It's really to show the water moving solitary wave. Okay. And this equation is integrable. So not only this solution, many solutions can be generated, and there is a general method to do this. So this. So we say that the KdV equation is integrable by the method called the inverse scattering transform. And this is one of the most famous method in the field of integrable systems. let me just cite the name of people that involves in this. So this method is a method to solve initial value problem. So you need to provide an initial condition for this. So the initial condition, I mean, so like at t equals 0, so you need to provide a profile at t equals 0, and then you can use this method to generate solutions that depends on t. So this method was developed by several people. Let me just give the name here. So the main ingredient for the method was developed by Gelfand, Leviton, and Marchenko. And it was presented in their paper in this years. Then it was Gardner, Green, and Pascal, and Mirror, who used it to generate solutions of the KDV. Okay. So let me give you another example of integrable systems. So this one, I picked this one because it's model. It's interesting because it's model physical phenomenon. But another one, which is called, another one is called the Sine-Gordon equation. This one appears in the context of differential geometry. Sine-Gordon equation. Oops, sorry. This equation here is a partial differential equation of two variables. Again, like the KDV. And this is for Sine-Gordon. This is sine function. Okay. It's so it appears in the study of surfaces in R3 with constant negative Gaussian curvature. Sorry, I write it longer than it should. Let me just try to make it here. Negative Gaussian curvature. Okay, so this one is also integrable by the inverse scattering transform. So inverse scattering transform can also be used. can be used to solve. Oh, sorry, I just happened to. Okay. Can be used to solve this equation, and it has to be the initial value problem. Can be used to solve an initial value problem. For the Songkla. And there is also another method to generate many solutions, which I want to present here, because I think it's quite nice and yeah, it's quite nice, this method. Let's see. Initial value problem. Okay. And the other method I want to show you is called background transformation. So this is a way to generate a new solution from a known one. So I will use it. This generate a new solution from a known one. If you know one solution, then you can use this transformation to construct more. Yes, so let me show you this. To do this, first I have to change the coordinates. So let say tau bx plus t over 2, and rho is x minus t over 2. Then you can show that this equation will become this one. In tau rho coordinates. Okay. And the background transformation is this. So it is a relation. It is two equations. Let me just. So background relation for the Songkla. Let me write it down, then I will say what the symbols are. There's one equation and there's another equation. Okay. So what these relations mean? It says that suppose you have a solution. Suppose you know a solution of the Songkla, say phi naught. Then if you can find another function phi1 that satisfies this equation, that is a solution to this equation, when you plug phi naught in, then this phi1 is also a solution of the sine-Gordon equation here. And this system of equation is easier to solve than, because it's first order, and this one is second order. And you can try, I have one example, but first, before I give you an example solution, let me write down just one line to say that why if, you know, phi1 satisfy these two equations, and it will be a solution of the sine-Gordon equation. It is this, because if you if you say differentiate the first equation here with respect to tau, yeah, with respect to tau like this, then here you will have a second order derivatives, like this equation. And for on this side, you will have a derivative in tau. But if you use this equation, it's possible to show, and I will ask you to verify this. So, to show that phi naught and phi 1, if you do like what I said, then you will have that phi naught and phi 1 satisfy this. So this precisely says that if phi naught is a solution, then this term and this term just go, right? Because if the phi naught is solution, is satisfy the sine-Gordon, so you don't have these two terms. Then phi 1 necessarily satisfy the sine-Gordon equation as well. Okay. And let me give you an example of a solution. So this is an easy example, because one very simple solution of the sine-Gordon equation is the trivial solution, the zero function phi is 0. Yeah, so the phi equals 0 satisfy this equation as well. Then you can pick phi naught to be 0. Okay, and put it in here. Then you can integrate this first order equations. I'd like you to try it yourself, and then you will have that. You will have a solution, another solution to the sine-Gordon, which is this one. Okay, where C and B are constants. Maybe I should write it. Since here, that backroom relation like this, where B is a constant. Is a constant, and here C is a constant too. It's a constant of integration. C is also a constant. Okay. Right. So so these are two examples of integrable systems that I'd like to show you. That so let me just kind of doing a summary again, that integral systems are differential equations that can be solved analytically, and I mean as opposed to numerically. And there is kind of a, you would say that an equation is integrable if there is a general method that you can use to construct solutions. And I show you two equations, which is, in fact, two of the most famous equations. The one is a KdV, that is describes a physical phenomenon, the solitary waves, and it's integrable by the method of inverse scattering transform. Then you have sine-Gordon equation, which appears in the context of differential geometry. And this one is also integrable by inverse scattering transform. And also there is this Backlund transformations that you can use to generate solutions as well. With one example, show you. Now, why we look at, let me just, why and what are the relations between integrable system and anti-self-dual equations, as in the title of this course. So, this, I think, one of the motivations to study the relation between these two is that there is really no universal definition of integrable systems. As you might see from my examples, that when I say that an equation is integrable, then I have to say that it is integrable by this method. Yeah, and there might be a solution that it is integrable by another method, that you can use this method to construct solutions, but then it might not be integrable by another method as well. So then because of this, it would be nice then if one could find a framework that includes many integrable systems in that framework. That you say that, okay, you define there is this way to construct solutions, and then in this way, many integrable systems that non-integrable system can be solved by it within this framework. Okay, and so that's where anti-self-dual equation comes in. So let me just write down a bit of what I said. So there is no universal definition. Let me just use abbreviations, a definition for integrability. By this, I just mean that, so no known so no universal method for generating solution of all cases. For generating solutions, let me just abbreviate, that cover all cases. Then if we can't find the one that cover all cases, we just maybe look at some framework that cover many. So look at a framework that covers many non-integrable systems, and this is where anti-self-dual equations come in. So let me write this idea in a diagram. And let me abbreviate anti-self dual by ASD. ASD, anti-self dual. So you have anti-self dual equation in 4 dimensions. And I mean the 2 equations I just mentioned, that is the anti-self dual Yang-Mills equation and anti-self dual condition for conformal structures. And these equations, they are integrable themselves as well by it's integrable. By twistor method. And let me just be clear that so we by anti-self dual equation, so you have the anti-self dual Yang-Mills equation and the anti-self dual condition for conformal structure. Let me just write that anti-self dual conformal equation. And it was observed by Richard Ward that many non-integrable systems can be realized as reduction of these 2 equations. So this equation is in 4 dimensions, and by this I mean, well, you could think of it that there are 4 independent coordinates for the equations. Then it turns out that there are many integrable systems in lower dimension. So they have fewer independent coordinates. For example, like the KDV and the sine Gordon we just looked at. Yeah, so these 2 equations, yeah. So this one and this one. So there are only 2 independent coordinates. I would say they're in 2 dimensions. And many of integral systems can be realized as reduction of these 2 equations. So on this side, from the anti-self dual Yang-Mills equation, you have an equation, a class of equation called solitonic equation. By this, I mean equations that emit soliton solutions. And soliton solutions are solutions that very roughly speaking, has profile which are preserved, like the moving solitary wave that you just saw. Like so, for example, both the KDV and the sine Gordon, the equation that we just looked at, both of them can be realized as reduction of anti-self dual Yang-Mills equation. And on this side, you have another class of integrable equations called dispersionless equation. An example of well-known dispersion-led equations that are reductions of anti-pseudo-conformal equations, or the DKP. And I will write down what this abbreviation stands for. And another one is SU infinity total equation. Both, oops, sorry. So both equations are what you say, they are very important in the study of geometric structures in differential geometry. And DKP stands for dispersionless. So this one is dispersionless case Tromsø P. Petviashvili equation. I might don't have enough space. Tromsø Petviashvili equation. Okay. So so to summarize, anti-pseudo equations, they kind of provide some frameworks that cover many known integrable systems that can be realized as reduction of these two equations. So by reduction, you have the lower dimensional integrable systems, and it turns out that this method, the twistor method, which can be used to generate solutions of anti-pseudo equations, the equation downstairs also inherit this method as well. And so it kind of serve as an umbrella, say, anti-pseudo equations, so an umbrella that cover many integrable systems. Okay, and let me just give you some references. So these relations between anti-pseudo equations and integrable system was first observed and presented in the paper by Richard Ward in 1985. And then it was extensively studied and accumulated in a book by Mason and Woodhouse, which it is in the reference page I showed you earlier as well, the Mason and Woodhouse. So in their book, they present a detailed exposition of reductions of anti-pseudo-Yang-Mills equation and also anti-pseudo-conformal equation as well. It is this book here, maybe I should. It is the second references. Now, this is a kind of introduction. Let me give you an outline of this course for 4 days. Come back to here. So the outline for the lectures. So I have three main kind of chapters that for the first one, starting today, I should say that due to the time limit, I will be in this lecture talking only about this side of the diagram. So in particular, look at anti-pseudo-Young-Mills equation. In fact, starting from defining it, what it is. And then I will look at some examples of reduction. Yeah, and look at how, and I will show an example of how to generate solutions in within this framework too. Yes, and yes, I'm not sure I will have time to go on to this side, but let's see. Right. So the outline. So for the first chapter, I will try to define what anti-pseudo-Young-Mills equation is. I will actually start from the very beginning, so to giving a summary of mathematical background that involves in defining this equation, and then so this might take today and perhaps tomorrow, and then I will look at examples of reduction of the anti-pseudo-Young-Mills equation. And an important feature of the anti-pseudo-Young-Mills equation, which is the lattice pair, which in fact underlies the integrability of the equation. And then the last chapter, I will try to say a bit about twistor theory, but perhaps only the rough idea that so this is based on the lattice pair. Actually, after I defined it, there is a geometric interpretation of the lattice pair for the anti-pseudo-Young-Mills. And then from this, I will try to present the idea of twistor correspondence. Which is actually, it would give a way to generate solutions of anti-pseudo-Young-Mills equation. Right. So next I will start. So this is the introduction, and I will now come to chapter 1, to define anti-pseudo-Young-Mills equation. But I think it is, yes, it's an hour now, so I think let's have a break. So I will start again. Let's have 7 minutes break, and I will start again at 3:05. Okay, let's continue. I think it's still recording, so let me share. Okay. So for this chapter 1, so it's anti-self dual, Yang-Mills equation. Okay. So what it is so roughly speaking, it is well, not roughly, it is a system of matrix PD. It is a system of matrix PD where these matrices are, they're really components. So what do I mean by matrix PD? I mean the dependent variable is a matrix whose entries are functions. Then you have a PD for these matrices, and in fact they are components. These matrices are components of the connection 1 form. Of the connection 1 form of a connection on the vector bundle. So the anti-self-dual Yang-Mills equation and the self-dual Yang-Mills equation is a condition on the connection on a vector bundle. Is a condition that you impose on connections defined on connections of a vector bundle. So to define anti-self-dual Yang-Mills equation precisely, I need to talk about connections on a vector bundle. And since I planned this course to be very introductory, like for first year graduate students, I will start from defining what a vector bundle is. Yes, but in order to do that, the prerequisite are basic knowledge on manifold and tensor field. Now, so I actually will start with recalling definitions and properties of manifolds and tensor fields from there. So I will start by, yeah, so this is like a recall. Manifolds and tensor fields. Okay. So in this part, I will well, give a summary, I think, of definitions, but starting from definition of manifold, and then define tangent vector, vector field, covector field, tensor fields, etc. But it will be, I'm afraid it will be only a brief summary, and I will just give statements. So there will not be proofs from this, but then the reference I referred you to, a reference I use for this one is the book by Lee on introduction manifold. The introduction to smooth manifold. I have to write the name because let me go back to my reference page again. Yep. So for mathematical background in differential geometry, when I prepared this lecture, I used these two books by Lee. Yes, and the one that I'm using about manifolds, this one, Introduction to Smooth Manifolds. Okay, let's start from what the manifold is. So I will writing quite informal, just to capture the main idea. So a smooth manifold, so it is a topological space that locally looks like Rn, so that we can, well, because when we do analysis, we start from Rn and we have calculus on Rn. Then in order to for manifold is a topological space that if you look closely, well, in a small region locally, then it's like Rn, then you can kind of do calculus on a manifold as well. Yeah, so this is a topological space. So when I say locally looks like Rn, more precisely, it which is locally. So looks like, in fact, it is homeomorphic to an open set of Rn. And let me just say that often we require that the topological space would have nice properties, namely this Hausdorff and second culture. But some authors omit these two properties. But in many examples, you will just have these two properties as well. Let me try to draw a diagram. So suppose this is your topological space M. So locally homeomorphic to open sets in Rn mean that you have kind of an open cover of M. What should I? Maybe let me just. Yeah, so you have like a collection of open sets in M that the union, sorry, the union of this collection is equal to M. Okay, and let me just draw. And then from this, and then from this open set, you have a homeomorphism onto an open set in Rn. Yeah, and you have this pair of U and phi that cover the whole M. Yes, so M is locally homeomorphic to open sets. So we could say that a smooth manifold is a pair where M is a topological space. And a collection of these pairs of U and phi, U and psi, I'm sorry. Yes, so this curly A, I mean the collection of pair, so of open sets in M, and then this homeomorphism. Well, so H U alpha is an open subset of M, and then it is an open cover, but the union of it is equal to M, and phi alpha is a homeomorphism onto its image. Okay. So this is precisely what is meant by being locally homeomorphic to open sets in Rn. So this each of these pairs are called coordinates. And the collection of all coordinate charts is called an atlas. And it defined a smooth structure. This one to define smooth structures. I'm sorry, I just well, let me say it again. So you have an atlas, and then in fact, it's not defining a smooth structure yet. You need a condition. Yeah? Let me just remove it for a bit. And so the condition is that if you have two U is, so the pair is called coordinate chart, and U is called coordinate neighborhood. And if you have coordinate neighborhood that overlaps, if say U alpha and finishing, if U alpha intercept U beta is not an empty set, so there is some non-empty overlap, then you would require, and this is part of a definition of smooth manifold, you require that this map which maybe I should draw it first before I write it down. No? Okay, suppose you have another coordinate neighborhood U beta here, that there's an overlap with U alpha. For beta. Okay, then the overlapping region, you say when you go down here, it mapped. This overlapping region is mapped by phi alpha and phi beta into this shaded area. Then you could consider this map from the gray region, from the, which is, I'm sorry, which is a map from here to here would be you go up and then go down again. So it's phi alpha inverse and then composite for beta. Okay, so it this one that I was about to write. Yeah. Yeah, so the condition for smooth manifold is that this map which map from this gray region on the left, which is the image of the overlapping region. I'm sorry, I'm not sure. I'm not sure whether the microphone is okay. Just to. I hope it's okay, but let's continue. Okay, I'm sorry, let me just check whether the microphone is okay. Yes, it is.
Yes, ma'am, it's okay.
Okay. Can you hear me? Anyway, I think from the computer it should be all right. Let's just continue. Right. I have to go back to my. Okay. So this the condition for smooth manifold is that this map, which is mapped from this gray area here. So it is the image under phi alpha of the overlapping region. And to the gray area on the right. So this is one. So it is required that this map is a diffeomorphism. And which is it is a smooth bijection with a smooth inverse. And it is well defined because it this map is a map between open sets of Rn. So smoothness is well defined here. And the map is called, this one is called transition function. And it is important that for our index alpha beta, that the coordinate neighborhood, the overlapping region is not an empty set, that this transition function is a diffeomorphism, because it will enable us to define smooth function on a manifold later. Otherwise, there will be inconsistency. So it's transition. Okay. Right. And this is a definition of a smooth manifold. And with now this is what I just A is called an atlas, which is a collection of coordinate charts, which is a homeomorphism like this. But then with this condition, then this atlas, we say that this atlas defining a smooth structure. Okay, right. And an example of a manifold, and the easiest one is this Rn itself. Yes. So what I'm writing here, I'm trying to writing M and A, right? M, so the topological space is Rn, and you can define a smooth atlas on Rn quite simply. That is this. Yeah, so A is a collection of coordinate charts, and we can just use a global chart that is we use this open set to be the whole M, which is Rn, and the identity. So this atlas consists of one single chart, and it is clear that it is a homeomorphism. Yes, and we don't need to worry about the transition function because there's only one chart. Okay. So this is the definition of a smooth manifold. Now, later, I will be talking about complex manifold as well. So let me just give a definition now. Maybe before I write down, let me just try to explain from the diagram. So for a complex manifold, then suppose you have this smooth manifold, but if n is even, yes, if n is even, say, okay, let me just jot it down a bit here. If n is even, then you can write n as 2m, yes, and this can be identified. I'm sorry with my equal, but yeah, informally this can be identified with Cm. Then a complex manifold is just the structures like this, that you have coordinate charts, that an open set is homeomorphic, but instead of to Rn, now it's to a complex, an open set in the complex space, Cm. Then we require, then this transition function would be mapped from Cm to Cm, and we require, instead of being diffeomorphism, we require it to be biholomorphic, that it is a holomorphic map, a holomorphic bijection with holomorphic inverse. So let me write this down. So if n is 2m, if n is even, so we can identify or 2m with Cm, then if the transition functions here is biholomorphic, so if all the transition functions are biholomorphic, then M is a complex manifold. Then M is a complex manifold. Okay. Now with on a smooth manifold, on a smooth manifold, we can define smooth functions too. So let me come, I'm sorry, so from, we will see a complex manifold later, but let me come back to a smooth manifold. And because of this, I'm sorry, and because of this, because of the fact that these transition functions, or the transition functions are diffeomorphism, then this allowed us to define a smooth function on a manifold like this. So the smooth, let me say smooth on a manifold. And maybe let me refer you to a proper definitions from the reference, but let me just try to say what it is by drawing diagram. For example, if you have a smooth manifold M, yeah, and you have a function f. F is a function from M, say to K. To a Euclidean space. Then we would say that this function f is smooth if since we only have the definition of smooth function on Euclidean space, right? But then for a smooth manifold, you have that the smooth manifold is covered by coordinate chart, which is, let me just write as a pair, which is homeomorphic to an open set in Rn. Then instead of F, then instead of F, we can consider this map. From here to here, which is a map between Euclidean space, and it is this is for inverse composite vector. Yes, and we call this map a coordinate representation of F. Coordinate representation of F. Then we say that F is smooth if its coordinate representations in any charts is smooth. If its coordinate, let me abbreviate it, representation in any chart is smooth. And this definition is well defined just because the transition function, just because of this condition here, that the transition function is a diffeomorphism. Yeah, because of this, this definition below is well defined. You just note, so it's well defined. Because the transition function is all transition functions are diffeomorphism. Okay. Right, and you can define smooth maps between manifold as well. And you see for this one, the function is from manifold to Euclidean space. So you only need to use coordinate just on this side. But if you have two manifolds, then of course on this side you can come down to with coordinates, and then you have a coordinate representation too. Then you just draw it just in diagram. Yeah, you have two manifold M and M. Oh. And you have a map F between them. Then we say that we would say that F is smooth if at each point in M, each point P in M, you can find a coordinate chart such that that you can find coordinate charts, and then this is the image in Rn in the Euclidean space. Then on this side, the map F would map point P to a point FP. Then if you can find coordinate charts on M and also on N, say V and psi. Yep. Such that if map this U here is contained in here, if U is contained in here, yes, then you can define a map from these two open sets in the Euclidean space. Yes, and this is given by, so you go for inverse, composite with F, and then go down with psi. Yes, yeah, the reason we need if map U inside V because of this, because we will composite with the psi. Yes, and we call this a coordinate representation of F, and then F will be said to be smooth if the coordinate representation is smooth. Okay, so now let me just end about manifolds and smooth map with this and go on to tangent vector fields, because in fact we have quite a long way to go. We have to continue from the time continue tomorrow. So I would like to recall definitions of vector fields and tensor fields and then differential form before we go on to define vector bundles and then Andy-Selder-Young-Mills equation. So let's continue until 4. So the next concept I like to recall is tangent vector field. So what is it? So suppose you have a smooth manifold, And let me use the infinity m to denote the set of smooth functions. Now the tangent space. To m have p at each point. Well, maybe I should say that well, if you haven't done, even if you haven't done manifolds before, then you would have seen a concept of tangent space, like at least in one-dimensional calculus, you have a line and then you have the tangent line. Yes, this is a line is also, you can show it is a manifold, and this is a tangent space at a point on the line. So, and say if you have a sphere, then at each point you have a tangent plane on a sphere. So this is a tangent space. So for an abstract manifold, then a tangent space at each point P, and we denote it like this TPM. So it is the vector space so we define it to be the vector space of linear map. So it is a linear map that map. Let me use the symbol capital X and with subscript P. As it's this linear map, which map a smooth function to a real number, satisfying a product group, such that it obeys this product group. So on the left-hand side, so the product of smooth function is smooth function. So this gives you a real number, and then this will be equal to this real number. Okay, which is just the product rule. And so each map, each linear map, we call it tangent vector. At the point P. In fact, it can be shown that if for the manifold, like for curves and surfaces which are manifold in R3, then there is a way to identify these tangent vectors that define like this with the usual tangent vector that you would think of in calculus, like the vector that is tangent to the line, for example. Okay. But this is a definition that we can use with any abstract manifold. Okay. Now, So with the time I have, let me just give an example of a tangent space of a tangent vectors. An example of a tangent vectors that we will use a lot later as well are the coordinate vectors. Coordinate. To define this, maybe I should draw some diagram. So you have a manifold. Okay. And at each point on a manifold, say point P. Yes, attached to each point P, you have tangent space. Let me just draw it like like this. So attached to each point P, you have a vector space for the tangent space, which is space of linear maps with this property. Then an example of an element in TPM are coordinate vectors, which is defined like this. Because well, M is a manifold, then each point each point is contained in a coordinate chart. Yes, and then this is the image under the image of the coordinate neighborhood onto here, and P is mapped to a point on Rn, so phi P. Okay, and the coordinate vectors and I will use a symbol, which is a partial derivative. I have to say that suppose in this the coordinate in these regions are x with the index a. Yeah, a is from if this is Rn, a is from this is x1 to xn. So with these coordinates, then the coordinate vectors denoted like this. And let me just to say that it is attached to the point P. The coordinate vectors is defined like this, so by definition, it is a linear map that acts on a smooth function and give you a real number. So so we have to define it by this action. So we defined it that it acts on a function and give you a real number, right? But this real number is the same as the partial derivatives of the coordinate representation of it and evaluated at this point for P. So you have a real valued function f on defined on M and then map to its real value is mapped to R, then you can consider this coordinate representation of f, which is a function from Rn to R that you can take the partial derivative. Then you just take partial derivative of this function and then evaluate it at this point. This gives you a real number, and you justify coordinate vectors by this action here. Now, and let me end today because this time is nearly over. So let me end by an important result that I will use later. That the set of coordinate vectors form is a basis for the tangent space. So the set is a basis for tangents. Okay. Right, and I think this it's just 1 minute. Let me just say that for tomorrow, I will continue with recalling these definitions. So now we have manifold tangent vectors. The manifold and tangent vectors at a point. And now, so tomorrow I will continue by reminding what tangent vector fields are, and then continue to tensor fields and the rest from there. Yes, so I think so this would be the end for today. So thank you.